we live by it every day. Our alarms, our meetings, our calendars all obey it. But time was never obvious. In fact, for most of human history, it was invisible. Humans didn't know hours, minutes, or seconds, they only knew events. The sun always rose in the east. It climbed high at midday. It disappeared in the west, but something else was happening. The sun did not rise at exactly the same point every day. Over many months, its rising position slowly shifted north, then south. That was the first discovery of seasons. Ancient farmers in Mesopotamia and Egypt realized that when the sun rose farther north, days became longer and warmer, crops grew. When it shifted south, days shortened, cold returned. They weren't measuring time yet, they were reading cycles. Night brought another pattern. The stars moved in predictable arcs. Certain constellations returned at the same time each year. The flooding of the Nile, for example, closely followed the appearance of the star Sirius in the Egyptian sky. This understanding of time through sky events was changed by a simple idea called shadow stick. If you place a straight stick upright in the ground, it casts a shadow. As the sun moves, the shadow moves. This was the shadow stick, the earliest known time measuring tool. At sunrise, the shadow was long and stretched west. At midday, it became shortest. By evening, it stretched long again toward the east. Ancient Egyptians began marking the ground where the shadow fell at different times of day. The shadow stick was a breakthrough, but it had limits. It showed movement, not measurement. There were no markings, no fixed divisions, no consistent way to say exactly how much time had passed. It depended on observation rather than structure. By around 3500 BCE in Egypt and later in Mesopotamia, people refined the idea. Instead of simply placing a stick in the ground, they began adding marked lines around it. These markings corresponded to recurring shadow positions at different times of day. Now, the shadow wasn't just moving, it was crossing defined segments. This transformed a simple observation into a calibrated instrument, the sundial. The sundial didn't just show that time was passing, it divided the day into measurable parts. The shadow stick discovered the pattern. The sundial turned that pattern into a system. By around 3500 BCE in Egypt and later in Mesopotamia, people developed the sundial. A sundial uses a raised pointer called a gnomon to cast a shadow onto a marked surface. Those markings represented divisions of the day. Early Egyptian sundials divided daylight into 12 parts. But here's something most people don't realize. Those 12 hours were not equal. Summer hours were longer, winter hours were shorter, time stretched and shrank with the seasons. To Egyptians, that wasn't an error, that was nature. They even used shadow length to schedule labor. Work began when the shadow reached a specific stone marking. Midday rest happened when the shadow became shortest. Work ended when the shadow crossed another marked point. The sun literally governed productivity. Egyptians even erected massive obelisks, towering stone pillars. As the sun moved, the obelisk's shadow swept across the ground. Priests marked its positions. They divided daylight into 12 parts. But even sundials had limitations. Shadows disappear after sunset. That created a new problem. Around 1500 BCE, a solution appeared. The water clock, also called a clepsydra. It was simple but brilliant. A bowl with a small hole in the bottom allowed water to drip out at a steady rate. Marks inside the bowl indicated passing time. As water drained, time passed. Water clocks were used in temples, courts, and astronomical observations. Priests used them to time rituals at night. Unlike sundials, water clocks did not depend on sunlight. For the first time, humans could measure darkness. While Mesopotamians measured flowing water, Egyptians looked upward. They developed the merket, a star alignment instrument. By aligning two merkets with the North Star, priests tracked specific stars crossing the sky at night. Time was now measured not only by the sun but by the stars themselves. With the merket, Priests could measure hours at night, giving them a complete 24-hour sense of time. They could record star positions, track seasons, and study constellations, laying groundwork for astronomy. Around 1800 BCE, mathematics started playing its role in time measurement. The Babylonians inherited Sumer's water clocks and Egypt's solar knowledge. But they added something transformative: numbers. They used a base 60 system. That is why today we still divide 60 minutes in an hour, 60 seconds in a minute. Without realizing it, we live inside Babylonian mathematics. They also tracked lunar cycles carefully. Months were based on the moon. But lunar months didn't match the solar year perfectly, so they added extra months to realign seasons. This was one of humanity's first attempts to correct time drift across the ocean. There was another civilization working on precise time measurement around 1000 BCE, the Maya of Mesoamerica. While other civilizations used shadow sticks or water clocks, the Maya measured time in a different way, using buildings, math, and the stars. One of their earliest timekeeping structures was the E group complex, found at sites like Uaxactun. From a western pyramid platform, priests observed the rising sun align with specific eastern temples during solstices and equinoxes. These stone alignments functioned as horizon based solar calendars, marking seasonal transitions essential for agriculture and ritual life. But the Maya did not rely on architecture alone. They developed complex calendar systems: the 260-day Tzolk'in, the 365-day Hab, and the long count calendar, using a base 20 number system and one of the earliest recorded uses of zero. Their calculations, preserved in texts like the Dresden Codex, include detailed tables predicting Venus cycles and eclipses. For thousands of years, time belonged to nature. The sun cast the shadow. Water dripped, incense burned, stars crossed the night, but something was changing. Cities were growing, trade was expanding, empires were stretching across continents, and nature was no longer precise enough. In European monasteries, a breakthrough appeared. Instead of water or shadow, engineers used gravity. Heavy stones were tied to ropes. As gravity pulled the weights downward, gears turned. But uncontrolled motion would spin too fast, so inventors created something revolutionary: the escapement mechanism. It released energy in small controlled ticks. Tick, pause, tick, pause. For the first time, time moved in equal steps, not flowing like water, not stretching like summer sunlight, but dividing evenly. The earliest clocks didn't even have faces, they simply rang bells. The entire town heard time pass. What makes this story extraordinary is that other civilizations, completely isolated, were solving the same problem. In ancient China, palace life required precise timing during long nights. They developed incense clocks. Carefully crafted incense sticks burned at predictable speeds. As sections burned, strings snapped and small bells rang. Some incense clocks were designed in complex patterns, so different scents were released at different times. Different hours of the night had different fragrances. You didn't check the time, you smelled it. The scent, sound, and smoke guided daily life, but this method was limited to a single room. Over centuries, Chinese ingenuity began to scale these principles, introducing water clocks, gears, and mechanical devices, predictable, observable processes that allowed continuous and precise measurement. Small experiments with gears and mechanisms laid the groundwork for larger, automated systems. By the 11th century, engineer Su Song built a massive, water-powered astronomical clock tower. Water flowed steadily, turning gears and driving a celestial globe, while mechanical figures struck bells and drums, signaling hours across the city. The same concept that once relied on embers and fragrance now harnessed engineering and mechanics, linking human observation with celestial motion. From personal incense clocks to citywide mechanical towers, China's journey of time measurement shows how innovation, mechanics, and astronomy merged. As European ships began crossing oceans, a deadly issue emerged. Sailors could calculate latitude using stars, but longitude required knowing the exact time difference between two locations. If your clock was wrong by minutes, you could be lost by miles. Ships wrecked. Lives were lost. In 1583, Galileo observed a swinging chandelier in Pisa. He noticed something astonishing. No matter how wide the swing, each swing took the same amount of time. This principle, called isochronism, meant regular motion could measure equal time intervals. In 1656, Christian Huygens built the first pendulum clock. It was accurate to seconds per day. Seconds, for most of human history, seconds didn't matter. Now they did. Pendulum clocks allowed accurate navigation, scientific experiments, coordinated military action, regulated factory shifts. Time had shrunk. Human life began moving faster. By the 19th century, every town set its clock by the sun. Noon was when the sun was highest, locally. But noon in one city was slightly different from noon in another. This was manageable until railways, trains traveled between cities rapidly, schedules required precision. If towns used different times, collisions became possible, and they did happen. The problem was no longer measuring time. The problem was agreeing on it. When railways expanded, train schedules became chaotic. In some cases, railway companies operated using their own private time systems. People carried conversion tables just to travel, because traveling 50 miles meant traveling into a different noon. In 1884, at the International Meridian Conference, nations agreed on time zones. The world was divided into 24 zones. Greenwich, England, became the prime meridian. Now time was global, not local, not solar, not regional. Civilization synchronized itself. For the first time in history, millions of people across continents lived by the same coordinated system. Humanity had standardized the invisible. As science advanced, especially physics, even pendulum clocks were not precise enough. Electricity, radio communication, and later computers required extreme accuracy. Quartz clocks, introduced in the 1920s, vibrated using crystal oscillations. They were far more stable than mechanical systems, but even quartz drifted. Then came atomic clocks in the 1950s. Instead of gears, instead of swinging metal, they measured vibrations of cesium atoms. Atoms vibrate at incredibly stable frequencies. 1 second is now officially defined by 9,992 Del 6,770 vibrations of a cesium 133 atom. Time was no longer mechanical, it was atomic. GPS satellites orbiting Earth rely on atomic clocks. They must account for Einstein's theory of relativity. Because satellites move fast and experience weaker gravity, time runs slightly faster for them than on Earth. The clock inside your phone ticks differently than the clock in space. Time is no longer just measured, it is corrected, adjusted, maintained constantly. Today, our clocks lose less than a second in millions of years, but the journey began with someone simply noticing. The shadow moved, and in that small observation, a revolution began.